Welcome to the Student Academic Learning Services Introduction to Balancing Chemical Equations video. In this video, we are going to define a chemical equation, learn how we balance these equations, and then look at an example. But before we get into the process of how we balance, we need to understand the reason why we do this. A chemical equation is a written formula that describes what's happening in a chemical reaction. A chemical reaction is a change that completely alters the chemical composition of a substance, and as a result, one or more new substances is created. The equation identifies the reactants or starting materials on the left, represented as uppercase A and B in this model, and the products or resulting materials on the right, as seen as uppercase C and D in this model. It also identifies the phases of the reaction participants, so whether they are solid, liquid, or gas, and this will show up as subscripts in your reaction. Either a G for a gaseous substance, an S for a solid substance, L for liquid, or AQ, which stands for aqueous, and that means that the substance is dissolved in water. Also, the reactants and products will be separated by an arrow, which represents the direction in which the reaction is proceeding. In this example, we have a two-way arrow, and that means that this particular equation is in equilibrium. But in most of your chemical equations, the arrow will be going from reactants to products in the forward direction. Finally, the number of molecules or moles of each reaction participant will be represented by numbers called stoichiometric coefficients. The lowercase a, b, c, and d in this model represent these coefficients, and in your chemical equations they will be whole numbers. The importance of these numbers results from the law of conservation of mass and charge, which is the whole reason why we need our chemical equations to be balanced. So let's investigate the purpose a bit further. Before we go through the method, let's briefly look at the purpose for balancing chemical equations. Remember that when substances get converted from one form to another, the rules of chemical bonding will take effect and will always be followed. So if we look at the example on the screen here, we have aluminum metal reacting with oxygen gas, and let's recall how we actually got to this product. In terms of chemical bonding, aluminum metal is in group 13 on the periodic table, so it carries a charge of +3, and oxygen is in group 16 on the periodic table, so it always carries a charge of -2. And if you remember the crossover method here, this 3 will be carried down here and the 2 down here, which leads to our product of Al2O3. This satisfies the chemical bonding rules. So our product is inevitably going to be aluminum trioxide. So here's where the problem lies. Let's look at the reaction again. On the product side, there's only one atom of aluminum and two atoms of oxygen, but on the right side, there's 2 atoms of aluminum and 3 atoms of oxygen. So as you can see, this does not satisfy the law of conservation of mass, and in order to do that we must balance the atoms on the left and right side so that there is no creation or destruction of mass. It's all going to be balanced. Now that we understand what a chemical equation is and why the process of balancing must be performed, we can actually perform the balancing procedure. As mentioned earlier, the numbers that we will be using in our balancing procedure actually reflect the number of moles of each atom in the reaction. In order to have a step-by-step approach for balancing any chemical equation, we're going to use the following 4-step process. Step 1, do an inventory of the elements in your unbalanced equation. Step 2, determine the atoms that are off balance and find their lowest common multiple, then adjust the equation accordingly. Step 3, check your inventory again and balance any other atoms that were already off balance or that became unbalanced during step 2. And step 4, repeat steps 2 and 3 until an overall balance is achieved and ensure the final numbers are in their lowest terms. Let's do an example now, and we'll just use the same equation as shown a few slides ago with aluminum and oxygen. Recall that we have aluminum metal reacting with oxygen gas, and the product formed is aluminum dioxide. The method is included in the upper right-hand corner in case we need to refer to it. The first step in our method is to do an inventory of all the elements in this unbalanced equation. So, if we proceed with that, we'll start with the left, and we see that there's only one aluminum, but due to the subscript of 2 on the oxygen, that means that there's actually 2 atoms of oxygen on the left. Then moving over to the right, or the product side of the reaction, there are, because of the subscripts, 2 aluminums and 3 oxygens. So right away you can notice an unbalance between the left and right side. 1 aluminum on the left, 2 on the right, and 2 oxygens on the left, but only 3 on the right. So we're going to have to proceed with our balancing procedure here. We've determined that both aluminum and oxygen atoms are off balance, and now we have to begin our balancing procedure. This presents a common challenge for many people, which is to determine which atoms to actually balance first. And there's so many different equations and no one way of going about it, so the best way to improve is to just do a whole bunch of practice and get better. However, I will share some balancing tips with you, and the first one is present in this example. If we look at the reaction, we have aluminum on the left side with no subscripts and it's standing alone, whereas oxygen has a subscript of 2. So aluminum is very, very simple, and balancing tip number 1 is to never begin with the easy ones. Start with the more difficult elements or atoms in your reaction, and that's a good starting point for balancing. So in this example, we are going to begin with oxygen. There are 2 oxygen atoms on the left side of the reaction and 3 oxygens on the right. So our task is to find the lowest common multiple between 2 and 3. And you may be able to do that in your head, that's fine. But for this example, I'm going to write it out. So for the number 2, the first few multiples are 2, 4, 6, 8, 10. And for the number 3, the first few multiples are 3, 6, 9, 12, and 15. So if we take a look at these 2, the common multiple between 2 and 3 then, and the lowest one, is the number 6. They both multiply into the number 6. That also is that there's an easy way to get to that number. You could just multiply the 2 by the 3, which equals 6. So if that works, then that gives you the lowest common multiple. Definitely use that method. Anyways, we've determined that the number 6 is the number that we need to get oxygen to on both the left side of the reaction and the right side. In order to adjust the actual reaction, we're going to be using coefficients. And coefficients are numbers that are placed in front of the reaction participants. We can't add or adjust the subscripts of a reaction because this would completely change the chemicals involved. So we'll start with the oxygen on the left, and we need to find a coefficient that will bring our total number of oxygens on the left to 6. And we already have 2, so if we use the coefficient 3, multiplying 3 times 2 gives us 6, so that will work here. I also have to update my inventory because I've now changed the number of oxygens on the left to 6. And now we'll move over to the right. The oxygen in this compound has a subscript of 3, so we know right away that the number 2 if you multiply that by 3, also gives us 6. So we need to update our inventory for the right now. And I'm going to show you right now that because we've placed the coefficient in front of the whole compound, we've also adjusted aluminum. So to find the new number for aluminum, just times the coefficient, number 2, by the subscript on aluminum, number 2. So 2 times 2 is 4. And the same thing for oxygen. 2 times 3 is 6. So check your inventory now and you'll notice that you've balanced oxygen, which is great. Unfortunately, aluminum has been altered and it still isn't balanced. So that's our next step then, is to move on and balance our aluminums. Based on our inventory, there are 4 aluminums on the right side of the reaction and only 1 on the left. And we can fix this very simply by bringing the number of aluminums on the left up to 4. And all we have to do is use a coefficient of 4 in front of the aluminum in the reaction, and that's not going to affect anything else, so it's a very simple fix. And then we'll update our inventory because now we have 4 aluminums. And look at that, aluminum is now balanced. It looks to me like there's overall balance of the equation. So the final step is to just ensure that your coefficients are in lowest terms. And number 4, 3, and 2 are all involved here. You cannot divide those to make them any more reduced. So we've definitely achieved overall balance and everything is in lowest terms. So great work. We've successfully applied the balancing method to an example and also learned balancing tip number 1, which is to start with the more complex reaction participants if you can. This concludes our video on the introduction to balancing chemical equations. If you have any questions on the material covered in this video, I encourage you to come by the SALS Center located in room 204 of the Student Service Building and make an appointment with the appropriate learning skills advisor. Thank you very much for watching.